The void of deep space stretches across distances incomprehensible to terrestrial understanding. Reaching beyond the inner solar system, let alone to other star systems, necessitates propulsion systems capable of sustained, efficient acceleration. Traditional chemical rockets, powerful for launch, struggle with the fuel demands of multi-year voyages. The fundamental problem lies in the tyranny of the rocket equation, exponential fuel mass required for increasing velocity to transport significant payloads to Mars, Jupiter, or even farther within reasonable timescales, demands a method that offers both high exhaust velocity and minimal propellant consumption over extended periods. Enter the ion thruster, a technology designed to overcome these deep space limitations. Unlike chemical propulsion, which relies on rapid combustion, ion thrusters generate thrust by accelerating a beam of electrically charged particles. This system prioritizes efficiency and endurance over brute momentary force. At its core, an ion thruster utilizes an inert gas, typically xenon, as propellant. Within the thruster chamber, electrons are introduced, colliding with the xenon atoms. These collisions strip away outer electrons, creating a plasma of positively charged xenon ions and free electrons. This ionization process is critical. Once ionized, the positive xenon ions encounter a series of electrically charged grids. These grids generate an intense electrostatic field, precisely engineered to accelerate the ions to extreme velocities, often exceeding 30 kilometers per second. This high exhaust velocity is the key to their efficiency. As the highly energetic ion beam exits the thruster, it must be neutralized. An electron emitter, known as a neutralizer, releases electrons into the beam, recombining with the positive ions. Without this neutralization, the spacecraft would accumulate a negative charge, eventually pulling the positively charged ion beam back, negating thrust. The continuous expulsion of these neutralized, high-velocity ions generates a minute, yet constant, thrust. Adhering to Newton's third law, every action has an equal and opposite reaction. Over weeks, months, and years, this persistent push accumulates, gradually propelling the spacecraft to immense speeds across vast cosmic distances. The power for an ion thruster system typically originates from solar arrays. As spacecraft venture further from the Sun, where solar insolation diminishes, more advanced power sources like radioisotope thermoelectric generators, RTGs, or even compact fission reactors become necessary. Electrical power is paramount for creating and accelerating the ion beam. A crucial advantage of ion propulsion is its incredibly high specific impulse, a measure of how efficiently a rocket creates thrust from propellant. While chemical rockets achieve specific impulses in the hundreds of seconds, ion thrusters routinely reach thousands, meaning they extract far more momentum per unit of fuel mass. This high specific impulse translates directly into vastly reduced propellant requirements for a given mission. A mission that might demand tons of chemical fuel could accomplish the same delta V, or change in velocity, with only hundreds of kilograms of xenon using an ion drive, freeing up mass for scientific instruments or habitats. However, ion thrusters are not without their operational trade-offs. The thrust generated is extraordinarily low, often measured in millinewtons, equivalent to the weight of a sheet of paper. They cannot overcome significant gravitational forces or provide rapid acceleration for planetary escape or urgent maneuvers. Therefore, ion propulsion systems are best suited for missions that allow for prolonged, gentle acceleration. They are designed for the cruise phase of deep space journeys, where patience is a virtue and the continuous accumulation of velocity eventually leads to very high terminal speeds. The operational lifespan of an ion thruster is a critical engineering consideration. The constant bombardment of accelerator grids by high-energy ions causes slow but inevitable erosion. Mission planners must meticulously design for durability, ensuring the thruster can function for years or even decades without catastrophic failure. Over time, the cumulative effect of this persistent, gentle thrust becomes profound. A spacecraft starting with a low velocity relative to its target can achieve speeds far beyond what chemical rockets could economically manage, enabling shorter transit times to distant cosmic bodies like asteroids, comets, or outer planets. The Dawn spacecraft, for example, successfully orbited both Vesta and Ceres in the asteroid belt, utilizing its ion propulsion system to execute orbital maneuvers and transition between these two distinct celestial bodies. This demonstrated the unprecedented flexibility and efficiency of ion drives for multi-target missions. The operational profile of an ion-propelled spacecraft differs fundamentally from its chemical counterpart. Instead of short, intense burns, an ion drive operates almost continuously, its faint blue glow a constant beacon of propulsion. This sustained thrust allows for a gradual, but ultimately greater, accumulation of velocity over months and years. Consider the journey to the outer solar system. A chemical rocket might execute a series of gravity assists, slingshotting around planets to gain speed, a process dependent on precise planetary alignment. An ion thruster, however, can slowly spiral outwards, continuously adding kinetic energy to the spacecraft, largely independent of such alignments. This continuous thrust capability also simplifies trajectory planning in certain aspects. While chemical rockets require specific launch windows and ballistic trajectories, ion drives offer greater flexibility. They can compensate for minor deviations or adjust course over time, providing a more robust and adaptable mission profile for long-duration expeditions. On Earth, engines deliver immediate high-torque power for rapid acceleration. In contrast, an ion thruster's output would be imperceptible in Earth's gravity. Its true domain is the vacuum, where even the slightest persistent force, unopposed by drag, can eventually accelerate massive objects to speeds unachievable with traditional methods. The comparison with terrestrial propulsion highlights the stark differences. A car engine moves tons of metal quickly over short distances. An ion thruster moves kilograms of scientific instruments slowly, but relentlessly, over astronomical distances, pushing the boundaries of human exploration further into the cosmic expanse. Another system critical to deep space travel, often taken for granted on Earth, is radiation shielding. As ion-propelled spacecraft spend extended periods exposed to solar flares, cosmic rays, and the Van Allen belts, robust shielding systems are paramount to protect delicate electronics and eventually human crews. The inherent efficiency of ion propulsion extends the reach of robotic probes, enabling missions that would be prohibitively expensive or impossible with chemical rockets. It permits longer mission durations and the exploration of multiple targets within a single voyage, thereby maximizing scientific return from each launch. Despite their efficiencies, ion thrusters face inherent limitations. Their low thrust means they cannot be used for rapid deceleration or orbital insertion into highly gravitational bodies without extensive, prolonged maneuvers. The delicate dance of space exploration often demands both power and precision. The primary cause of wear in an ion thruster is the physical sputtering and erosion of the accelerator grids. Ions, though meticulously guided, inevitably impact the grid surfaces, slowly degrading their integrity. This erosion dictates the maximum operational life of a thruster, a critical factor for multi-year missions. Furthermore, the dependence on electrical power is a significant constraint. While solar panels suffice closer to the sun, deep space missions require more robust and compact power sources. The eventual decline in power output, whether from solar panel degradation or RTG decay, limits the thruster's performance over extended periods. The need for a heavy propellant like Xenon, though used sparingly, still adds mass. Researchers are exploring lighter alternatives like iodine or magnesium, which could offer similar performance at a reduced mass penalty, thus extending the spacecraft's effective range and payload capacity. Future advancements in ion propulsion focus on increasing thrust density without sacrificing specific impulse. This involves developing more efficient ionization chambers, designing erosion-resistant grid materials, and exploring alternative thruster geometries such as Hall effect thrusters or magnetoplasma dynamic thrusters. The long-term viability of deep space human missions will likely depend on hybrid propulsion systems. Ion thrusters could provide the primary cruise power, while chemical or even nuclear thermal rockets handle high-thrust maneuvers near planets or for emergencies, creating a versatile and resilient transportation architecture. Consider the vastness of the Oort cloud, a spherical shell of icy objects billions of kilometers from the Sun. Reaching this distant reservoir of comets within a human lifetime demands a propulsion system that can accelerate continuously for decades. Ion drives offer the sustained momentum required for such journeys. The sheer scale of interstellar distances renders current ion thrusters, efficient as they are, insufficient for star hopping. Even at tens of kilometers per second, reaching the nearest star would take tens of thousands of years. This reveals the limitations of even advanced current technology when confronted with truly astronomical scales. For true interstellar travel, ion propulsion in its current form remains a stepping stone, while revolutionizing solar system exploration, even accelerating to a fraction of light speed, requires energy levels and specific impulse far exceeding present capabilities. This marks the next frontier of propulsion physics. The evolution of space travel is a continuous story of overcoming limitations. From chemical rockets for orbital mechanics to ion thrusters for deep space cruising, each advancement pushes the horizon further. The problems solved by one technology inevitably reveal new, more profound challenges. The persistent, subtle push of an ion thruster embodies humanity's enduring quest to comprehend the cosmos. It represents a deliberate, methodical approach to traversing distances so immense they reshape our understanding of time and scale, transforming years into mere moments on a cosmic clock. In the silent, airless expanse, the faint blue glow of an ion drive signifies a journey measured not in immediate power, but in sustained effort. It is a testament to engineering precision, a mechanical whisper pushing tons of spacecraft across the profound emptiness separating celestial bodies. The operational lifespan of these systems, often spanning decades, means that the machines themselves become silent voyagers, enduring the harsh radiation and vacuum of space long after their terrestrial creators have moved on. They are enduring extensions of human curiosity. Each kilometer gained by an ion-propelled probe is a further unraveling of the universe's secrets, a slow but relentless expansion of our observational reach. The universe remains indifferent, yet our instruments, propelled by these ionized gases, diligently gather its data. The universe, an expanse of unimaginable scale, presents problems that demand equally grand solutions. Ion thrusters, by carefully managing energy and matter, provide an elegant answer to the problem of efficient deep space transit within our solar system. Their quiet efficiency enables a patient exploration, revealing the dynamic processes of other worlds and allowing humanity to gather data over extended periods, mapping and studying distant phenomena with unprecedented detail and continuity. As humanity gazes further into the cosmic void, the question persists: what new forms of propulsion will eventually bridge the chasm between stars, making the journey across light years a reality? And how will those advancements fundamentally redefine our place within the universe?